Hey, thanks everybody. It's really great to be here. Thanks for having us to speak at the HackFest this week. I'm going to try to advance these slides here. There we go. Matt, do you want to go ahead and introduce yourself first, and I'll go second and roll from there?
Yeah, sure. My name is Matt Wilhelm. I'm an engineer with Inferno Red Technology, working on the ElectionGuard project. Been building software for as long as I've been able to type, basically. And I think I'm also here to play tech bingo, and I'm just going to say Kubernetes and get it out of the way.
Great. Well, thanks, everyone. I'm Ethan Chumley. I'm a senior security strategist at Microsoft, and I work on our Defending Democracy program. It's the Defending Democracy program is chartered with the cybersecurity for campaigns, elections, and countering disinformation. We operate in the US, of course, with a focus toward the upcoming 2020 US presidential election, but across the world as well. Trying to take a holistic approach to security as it relates to a very important area, we think. So we'll just sort of start off with a little bit of background context, why my team exists and why this is such a hot topic right now. I think that in 2016, as everyone knows, there was sort of the United States' first introduction to cyber-enabled threats to democracy. Something that had been going on in various countries around the world, certain bloc countries, but in the US, we really opened our eyes to it in the 2016 elections. Among many efforts that were that happened, the Microsoft decided to spin up our program. So we wanted to see what we could do to help stop those cyber-enabled threats to democracy, what we can do to help promote election integrity, and that looks like helping to secure political campaigns to prevent hack and leak operations on emails and files. Looks at how do we stop the spread or slow the spread of disinformation or educate the public around some of the dangers of disinformation. But most relevantly to this talk, it also includes election integrity projects, of which ElectionGuard fits very nicely into. I'll just quickly on this slide, this top left headline, 2020 election won't look anything like we've seen before. That headline is about a year old, but man, is that correct? I think 2020 in general isn't looking like anything we've seen before, which makes this work even more relevant, I think. The challenge that we set forth to solve when we started the ElectionGuard project was to protect the integrity of elections, and specifically to protect the integrity of the vote. When we talk about that, we generally mean that we want the official tally at the end of the day, at the end of a voting process, to represent accurately the intent of each voter that went in to vote. In the US, we have sort of this one person, one vote concept, and we want to make sure that that is not interfered with, that is not meddled with, and that the intent of the voter comes through, and that cyber operations don't interrupt or interfere with that. You hear a lot of talk, and there's a lot of really interesting and complex and nuanced topics when it comes to voting and voting security. There is an almost religious battle around paper voting, voting on paper versus using electronic equipment. There is an equally sort of fierce debate around security versus accessibility. Generally speaking, I would say that those don't always have to be at odds with each other, but oftentimes they are pitted that way. And more recently, certainly in light of the COVID pandemic, there's a lot of discussion about in-person voting versus mail-in voting. All of these have many layers to them, and we could talk, for hours, and there are, many sessions around each one of these topics individually. But I think generally speaking, if we focus on ensuring the integrity of the vote, there are many solutions out there. There are many attempted solutions out there that some have been very effective, some have been less effective. Generally speaking, I think there's a lot of interest in moving the ball forward right now in a way that we haven't really seen before. So when we sort of approached this before we even had an idea of what the ElectionGuard project would look like in the end, we started with a set of sort of design principles, if you will, or a set of big ideas, right? We wanted to build something that was highly secure and highly vetted. We are, cybersecurity and democracy is in our sort of team's blood, and that's what we wanted to really shoot for, but we didn't want to just develop in a vacuum. We didn't want to just depend on Microsoft's engineers. We didn't want to just pull in really great other engineers like Matt that can write good and write secure software. We wanted it to be vetted as well. We wanted to engage the security research community, much like many of you, in order to further our project and further the security of it. Ultimately, this is a project that relates to voting, right? ElectionGuard needs to respect voters' privacy and it needs to respect voters' secrecy. This is not in any way supposed to be a system in which you can gain insight into how someone voted, and we can talk and we will talk about secret ballot elections here in just a moment. And maybe most importantly, what ElectionGuard is something that's end-to-end verifiable. An end-to-end verifiable election is a term that was coined by a researcher that currently works at Microsoft Research. His name is Josh Benelo, who wrote his PhD thesis called End-to-End Verifiable Secret Ballot Elections. And in large part, we have drawn on his great work and his great research and sort of brought that into fruition out of a research paper and into sort of the real world, if you will, through this project. I will talk about what exactly makes an election end-to-end verifiable. And it needs to be auditable. Just saying that an election was conducted correctly is not sufficient. We need to be able to prove that. There's a bullet point missing here that's also one of our principles, which is accessibility. We don't want to leave anyone out of the voting process in whatever it is that we create. So what is end-to-end verifiability? Or we'll call it E2EV for short. E2EV aims to answer the question of how can I trust the accuracy of an election outcome if I think that there could be a compromise in the software, hardware, or personnel responsible for conducting that election. Sort of certainly a big question. So what makes an election end-to-end verifiable? If at the end of the day, voters can verify that their own selections have been correctly recorded and included in the tally, but also that anyone can verify that all of the recorded votes have been correctly tallied. It sort of switches the idea of auditability and verifiability from the machines and the equipment that are doing the vote collection and the vote tallying to auditing and being able to get some transparency into the end result set at the end. There's an important note here that end-to-end verifiable elections can also be achieved by everyone walking up to a whiteboard and writing their votes next to their name. It allows a voter to verify that their elections have been correctly recorded and allows anyone to verify the tally. But unfortunately, we have the rather onerous problem of having secret ballot elections. So an election is secret ballot if nobody is able to know the selections of one particular voter. And that includes the voter themselves being able to be coerced into giving up their own vote or somehow showing that they voted that they voted a specific ballot. So our solution to this is a product that we're calling ElectionGuard. ElectionGuard is at its core an open source, end-to-end verifiable SDK that is meant to be deployed and run on elections hardware. It supports any style of elections, those that are primarily paper-based, those that are entirely electronically based. So long as there is an electronic component somewhere in the process, for typically around the tally or the collection of votes. You might think of a hand-marked piece of paper that somebody marks with a pen and paper and then feeds into a scanner, for example. So long as that scanner has an electronic component, the ElectionGuard SDK can be used. Before we go much further, I'll just sort of clarify here that ElectionGuard is at its core software and it is open source, and you want to work with existing voting manufacturers, existing voting equipment manufacturers to help secure and introduce end-to-end verifiability in their equipment. Microsoft is not getting into the business of making elections hardware. We're not making a full-blown voting machine that we plan to sell to states. We want to work with people that are already doing that and improve their process. In the background of this slide here, you'll see sort of a white what we call the pizza box. It's a off-the-shelf printer, an off-the-shelf Surface tablet, and an Xbox adaptive controller that we work together into what I think is a pretty nice design as simply a reference implementation. It is a piece of hardware that's in some of our offices. It's just a reference implementation to show off sort of the power of the software. It's hard to talk about software just in the abstract sometimes. But there's only a handful of those out there in the world, and we don't necessarily plan to continue to produce those. So we could talk for hours about the intricacies of ElectionGuard, but I will just sort of start by giving a high-level summary of some of the 4 key steps and the 4 key processes that you'll go through. The first is something that we're calling the key ceremony. So the crux and the basis behind ElectionGuard is secure and homomorphic encryption. And good encryption starts with good keys. And the key ceremony process, which I believe Matt will talk about a little bit, is how we start this. We call it a key ceremony because it actually brings a few people together. It brings trustees, administrators of elections together to generate one large encryption key, which is then split into pieces, and part of that key is given to each what we're going to call an election guardian in this case. In an ideal world, those keys are then stored offline in some sort of a secure key storage. Think of like a hardware key, like a YubiKey or something similar, or a smart card. So that generates then a public key that is used for the encryption of the votes themselves. The second column, homomorphic encryption, is the process being used, but generally speaking, you can think of this as the actual votes. You're walking into a vote center, you're voting, or wherever it is that you are casting your own votes. This is that phase sort of after election day begins, if you will. Once a voter makes their selections, each ballot is homomorphically encrypted, and then the unencrypted individual ballots are never stored or processed other than simply to encrypt them. Then the voters come through, everyone casts their votes, they're all encrypted, and then at the end of the day, those votes are tallied. And this is some of the uniqueness of ElectionGuard here, and I know Matt will speak to this in a little bit more detail, but the homomorphic tally, allows the final votes to be calculated without ever decrypting a single individual vote, which would violate some of the voter secrecy principles that we have. Importantly, not one individual person can decrypt the results of an election. It takes a quorum of some of those guardians to come together so that one rogue individual or perhaps one compromised individual is unable to decrypt the results of the election. And then most importantly, the public verification step at the end. During the voting process, each voter is given a unique tracking ID, satisfying the ability for them to go in and see that their vote is recorded as part of the final tally. And then the entire encrypted election record is published at the end of the election, which allows watchdog organizations or political parties or election authorities to go in and verify that no tampering occurred with those encrypted values using a set of mathematical proofs. So with that, Matt, I think I'll turn this over to you to go into the details of it.
Cool, thank you. So I want to get into the weeds here a little bit on this, but as Ethan said, there's an awful lot that we can cover. So I want to focus just on the way that the ballots are encrypted themselves, and then how the homomorphic encryption is used to generate those tallies, and just to kind of show what that looks like in code and what those data structures look like. So as you can see on the slide here, with traditional kind of static encryption like AES, you can't really do anything fancy with it. It can encrypt and decrypt values, but with homomorphic encryption, we can take 2 different encrypted representations and do essentially first or second grade mathematics on those things, and add them together, multiply them, and process a result from that and decrypt that result as if the result itself were encrypted on its own. So that ends up being really powerful for us in ElectionGuard. And what this allows us to do is take the individual selections on any specific ballot, add them together to form a total tally for the entire election for that specific selection. and then decrypt that value in that encrypted format without actually having to go through and traverse each one of the individual ballots and decrypt them. So this mechanism really helps protect the privacy of voters and the secrecy of the selections that they make, and just kind of generally lends more confidence to the election system as a whole. So let's take a look at how that works. Yeah, next slide. Cool. So here I have a fairly simplified code example of what it looks like to encrypt a specific selection. So what we expect to come in is the plain text representation of what the voter chose. That's going to be true or false, right? A 0 or 1. And we expect some metadata regarding that specific selection in order to verify that the selection is valid for a given contest and an election, and basically just make sure that the input data that's being provided to us is actually valid. And then we take the public key from the key ceremony that Ethan had mentioned earlier, and we use that when combined with a specific nonce that is really just a representation of randomness that we can use in order to generate the encryption for a specific selection on a ballot. So from there, as you can see, this function's actually pretty straightforward. We generate our encryption, and then we create a proof that that encryption is correct using a zero knowledge proof, and we'll get to that in a second. And then after we verify that that proof is correct, then we're going to return that to the caller. So what gets returned? Next slide. Shocking, it's an encrypted ballot. This is a representation of what gets returned back. The data structure is very similar to what would have been passed in, except that the plain text values that would have existed, we end up replacing those with the encrypted representations. And then we also add our proofs in there. We use a couple of different types of zero knowledge proofs throughout ElectionGuard, but specifically for the selections, you'll see here that we have a proof that the value that's encrypted is either 0 or 1, meaning that it's an encryption of true or false. And this protects against a malicious system sending in any sort of arbitrary value like 42, for example, right? And then down at the bottom, we have another proof that is a proof of ballot correctness. And that proof is it verifies that the sum of the selections that are made by a specific voter on a specific contest do not exceed the maximum. So also that all of the individual selections are either 0 or 1, and that there's not too many selections possible. And these two proofs together can give us a really high level of confidence that the ballot is well formed, and once it's been encrypted, it's actually not been tampered with. So if you want to pop on to the next slide here. What that means is that at the end of an election, we can publish the encrypted ballots, we can execute a tally homomorphically against all of those ballots themselves, and publish the tally that's in a decrypted state along with all of the mathematical artifacts that we use to generate that, and anybody can come by and independently verify that those ballots are well formed, that they're encrypted, that the proofs check, and that the sum they can run the tally themselves actually, since it's encrypted, and verify that the sum of those that the sum of the ballots themselves actually matches what the representation is that was done during the decryption phase. And I mean, that's great for independent verification from say, news media or watchdog groups or other members of the community. But of course, we don't expect, voters to go home and fire up their Python interpreters and, start writing some really heady mathematics in order to check that their ballot was included. So do you remember I mentioned that there's a secret nonce that's generated? It's just a random number. A representation of that gets encoded into this tracking ID that Ethan had mentioned earlier, that gets printed on this sheet that a voter takes home with them, and they're the only ones who have that value. That value does track with the ballot itself, and that's how we publish it, and that's how they're able to identify that that ballot exists. So when a voter goes home and those results are published, they can go and log into a website and they can check and see that their ballot was included. But what's really important here is that tracking code in there is not actually the private key. So you can't derive that, you can't reverse that backwards and then go and try to decrypt the ballot specifically. So there's no risk of that at all. It's a one-way hash. So that's most of what I have here, Ethan, unless you want to talk about spoiled ballots. Maybe we have time, but
if you'd like to, we've got some time if you want to talk about it.
Sure. So this whole mechanism right here, another thing that it does is there's this process that can be called challenging or spoiling a ballot, which is something that most jurisdictions, at least here in the United States, have for a voter to, if you fill in a ballot and you make a mistake and you want to go get a new one, that ballot that you filled in doesn't actually just get thrown away. That becomes part of the record that gets published as well. So what we're able to do is we're actually able to take that, and since it was not included in the tally results, that ballot, we can decrypt that ballot specifically and publish the clear text. And what's cool about this particular process, it's designed for mistakes, but it also allows a concerned citizen to actually go and fill in a fake ballot with very specific selections on it, and then spoil or mark that challenged and go back and vote for real as they normally would. And then when the election results are published, they can go and verify that we did our math correctly, because they know that their tracking code, what selections should actually be on that, because they wrote them down or knew ahead of time before they went in. And what's really cool about this is it forces the election system to be honest, because of course you can't know ahead of time who's going to come in or how many people are going to come in and try to do this process. So by definition, you have to kind of behave responsibly, which I think is pretty awesome.
Yeah. Dr. Josh Benoit, who we referenced earlier, is one that sort of pioneered this idea. It is known in the community as the Benoit Challenge, for those that have a background in cryptography. Anything else, Matt? Sorry, before I move on.
No, that's it. Go ahead.
Okay. So ElectionGuard is more than just a theoretical SDK at this point. We have conducted an election out in the wild. We did a pilot election in February, fortunately right before the pandemic hit, in a small town called Fulton, Wisconsin, where we actually deployed ElectionGuard software in partnership with a company called VotingWorks. VotingWorks is one of the newest election hardware vendors. They are a nonprofit based out of Silicon Valley. And they integrated the ElectionGuard SDK into their ballot marking devices. It's actually what you see on the right-hand side of the slide, is a poll worker setting up one of the ballot marking devices that's actually housed in a Pelican case. So we ran a successful pilot in February, and we acted in the case of ElectionGuard as a secondary tally, as we were still making sure that the system was trustworthy and worked the way that we were able to be certified for use in the state of Wisconsin, was as a secondary tally. So the VotingWorks equipment, someone would walk up to what's called a ballot marking device, a touch screen where they're going to fill their ballot. They would make their selections on the touch screen, and you would then walk over to a printer that would print out your pre-marked ballot on it. The voter would manually verify that the selections were correct on the paper ballot, drop that into a ballot box. So then there was a paper archive as well as the encrypted ElectionGuard vote that was stored on the device itself. So at the end of the day, we ran the ElectionGuard tally and we ran the paper tally, with the poll workers counting the paper ballots by hand. And of course, the results matched at the end of that. So a thank you to all of our friends in Wisconsin that helped make that possible. So we're coming up a little bit on time, and I want to be sure that there's time for Q&A at the end of the session, but a few more things here real quick. Being a penetration and a security testing summit, I want you to know that you can help all SANS participants, all participants everywhere, can help to validate ElectionGuard security. We have a bug bounty program. Microsoft and MSRC, the Microsoft Security Response Center, have put together a bug bounty specifically for the ElectionGuard code. We welcome security researchers to come, to poke, to find vulnerabilities and report them through the reporting process that we have set up. We pay anywhere from $100 to $15,000 for various classes of bugs, specifically around the security and the cryptography, being primarily a crypto-heavy SDK. If you're interested in learning more about that, there's a link there at the bottom. Feel free to hit that or send us a note, and we can let you know how to get involved in that. Like I said to start this off, everything we're doing is open source. This is not closed source software that we're trying to sell. This is open source software. It's all hosted on GitHub. The URL is right there at github.com, Microsoft ElectionGuard. There are a few, you will notice if you go take a look, different classes. There are many repositories underneath the ElectionGuard umbrella. And I think it's important just real quickly to call out, because I imagine many of you will go take a look at those. Some are the core cryptography. Some are those core services that do sort of the bulk heavy lifting of the ElectionGuard work. There's one around mathematical specifications that's pretty research heavy. And then there are a handful of demo implementation repositories as well. If you don't necessarily care about all the underlying encryption, you just want to use this service in a prototype voting system, we have a .NET Core web API that you can simply make API calls in and out of, and you don't necessarily have to understand all of the deep mechanics of ElectionGuard. There are various layers of abstraction, various setup and demo scripts there. At the top of the slide, we want everyone to come, please participate, research, but I do kindly suggest maybe waiting until next week. We are moving out of sort of our quote unquote beta phase into a full release on June 15th, which is in about 10 days from now. That source is currently in a private repository. It will become public very soon, and it'll become public once we feel we're at a good sort of 1.0 release state for that. So if you're really excited and you really want to contribute, thank you so much, please do, but your efforts will be much better spent once we do our next release about a week and a half from now. So I encourage you to do that. And once this latest code comes out, it happens to be written in Python, we're going to deprecate some of our existing libraries that we have up today that are primarily written in C. There's also anyone that works on encryption is familiar. Complex encryption requires a lot of compute power. So we tried to balance some of the needs of having high performance computing with the high performance of a modern laptop class processor versus the need of, say, smaller, more embedded style hardware that might run on something like a scanner that might be scanning ballots. So we are going to also later this summer come out with what we're going to call ElectionGuard Core, which is going to be a C++ based repository that will only do sort of the middle stages of ElectionGuard, which is the actual encryption, the key generation, and then the decryption will happen off that machine on something that's a little bit more powerful. So if you like diving into C++, give us till the end of the summer, and we'll have something more for you on that. There's a link there just to close this out. If you're interested in early access, we're not sure exactly if we're able to offer early access or not, but as soon as we sort that out, and if we're not, certainly we can put you on a list to be the first to know when some of this stuff comes out. So that's aka.ms/egnotify, ElectionGuard Notify. Feel free to sign up there. Give us your email address, GitHub handle if you'd like to be part of some of that. So Moses, I think that concludes the actual presentation part of this. I imagine there might be some Q&A. I'm not exactly monitoring the channels, but I turn it back to you.
There is a ton of Q&A. By the way, I should have prefaced this with, and I guess this is a great question just for me to you guys. Microsoft traditionally wasn't in the habit of selling election software, right? But it just so happened that many of the voting machines were using Windows underpinnings, right?
Yeah, generally speaking, yeah.
Yeah. So for those that have never played with like one of these voting machines, a lot of the ATM voting machine kind of systems underneath were Windows CE, Windows XP. It's hard to tell, I guess, at this point, what they could have been. But here's a question that I would have, right, for you guys, real quick before we get into the Q&A. From the standpoint of encryption or cryptography, as time progresses, do you see this kind of cryptography being less and less, I don't want to say efficient, maybe reliable, broken as time goes on?
Sure, thanks. I'll start by talking about Windows and some of the first things you mentioned.
Yeah,
and
sure.
I turn it over to Matt to talk about the encryption because I'm quickly out of my depth there. When we started this, you're right, Microsoft was not in the business of making or generally selling specific anything to the voting vendor market specifically, because we don't have intentions of going there, but we did see a need where, it was an industry that was getting a lot of scrutiny. It was an industry that we thought we could provide some expertise through Josh Fenelo and some other folks at Microsoft. We thought we could be really helpful. So that's sort of where ElectionGuard came from. The underpinnings, if you will, of voting systems vary. Some are Windows-based, some are not, some are Linux-based, some are custom completely. I will say we announced maybe 6 or 8 months ago, that through our team, if you happen to work at a voting machine vendor, or you know of a situation in which this can be helpful, we are offering free extended security updates for legacy operating systems that might be in use for the 2020 elections. So it's not always possible to retrofit a new OS this late in the game towards an election, but let's make sure you're getting the latest and greatest from our MSRC team on some critical Windows bugs. So you can message us if you work at a county or an elections organization. You can get free extended support updates for certified election hardware. Matt, I turn it over to you for the encryption question.
Sure. So the specific type of encryption that we're using is exponential algomal encryption, and it's going to have the same kind of risks that pretty much all other modern cryptography have, right? Like, I mean, if SHA-2 actually gets cracked by a quantum computer, like the entire internet has to be reinvented. You know what I mean? So from like, those are the primary risks that we would have. But in the shorter term, these things are pretty mathematically very difficult to brute force, right? So when you're talking about taking a large prime number to the power of another large prime number and trying to figure out the result and doing those factorializations similar to what you see in like the cryptocurrency or blockchain space, like it's kind of the same underpinnings that you have there, and similarly with the zero knowledge proofs. So I think the risk profile on the actual mathematics itself is very similar to everything else that we have. Basically.
But I would also think, and this is just speculation, but I would also think that if it takes you 180 days to crack, to basically forge your own ballot, but the election's only running for like 20 days, just, the time constraints that it would take to actually forge the ballot wouldn't matter, right? So you have to wait until that this type of encryption is basically almost forgeable by default, right? Within hours or minutes or whatever, before it's irrelevant.
Yeah, I mean, one of the risks, and Ethan can probably talk to this a little bit more, is coercion, right? So we want to protect the privacy of voters, and if those ballots are out there in an encrypted format, if they're published publicly and they are able to be decrypted at some point, there could be, social repercussions for an individual, and that's one of the things that we want to be able to protect against, is that privacy and secrecy. So,
all right, so a few questions. First one was really early on. How can you prevent voter fraud without using real ID? And I think the answer there is you're kind of creating your own voter ID system, if you will. Is that right?
I think the intent of ElectionGuard is to secure the votes once a voter is already voting. So we look to the states, and in the U.S. certainly each state or each county and municipality runs their own voter registration database, voter ID or verification checks. So we leave it up to the states to continue to take that on themselves, and then once the state has authorized somebody to vote and they're at a piece of election equipment, that's where ElectionGuard kicks in.
And of course, this is geographically, we think very U.S. centric here, but you're looking at it globally, right?
Absolutely, yeah. We have a little bit of a U.S. Focus just because the majority of our team lives and votes in the U.S., but there are absolutely international applications for this technology. Anywhere that has a secret ballot elections in some of the ways that have electronic components in the supply chain somewhere of the vote, this can be used in a number of other countries as well.
Yeah. There was a question about selling this, but it's an open source SDK, right? So I think that's
open source SDK. It's on GitHub, MIT license. Go for it.
Yeah. So I guess I might have sparked this one, right? But question was, why not use blockchain? And kind of how the end-to-end encryption works. But I think you may have answered that one live.
Yeah, so there's one more thing to say about that specifically, and that's that by definition, a blockchain is organizing transactions into a batch, right, and then committing them to a database. So if you were able to reverse the encryption, or if you take that tracking ID that we have, someone could look at the blockchain record and say that your vote was ordered in a specific order, right? And that's just kind of the nature of the blockchain data structure in and of itself. But when we do the tallying process, the ballots themselves don't actually have to be in any order. So it's not that blockchain couldn't be used, it's just that it doesn't get you anything. So there's really no point, basically.
I'll also add just on the blockchain point, it's a question we get a lot, and there's a handful of answers that are all relevant. One that's always stuck with me is that voting in the way that it is set up in the US and pretty much every country is inherently a centralized process. There is an election authority that runs elections. Voting itself is not distributed, much like the benefits of a blockchain become when it is distributed.
Yeah, and of course, not to say that processes couldn't change and that couldn't become a better solution, but for what we're working with municipalities now, it just really isn't really the right solution, unfortunately. And this is coming from a guy who's wearing an Ethereum shirt.
There you go, right? So I guess I should have asked earlier, the SDK, is it multi-platform or is it just Windows centric?
Yes, multi-platform. Linux is a first-class citizen here, along with Windows, and I myself develop on a Mac, so by definition, we've kind of got all three. But specifically for the C++ libraries, we're looking to target a kind of lower-end set of hardware. We're still working out some of the specifics, so please don't quote me on this, but we're looking for Atom-based processors for Windows 32. I know that's like really, really old. And then we're looking at a Raspberry Pi 3 essentially on ARM to represent the lowest level that we would want to go. And we want the encryptions that we do to be very performant on those pieces of hardware. And we think that if we can hit those targets, then it becomes kind of a very difficult for an election system vendor to use performance as an excuse not to implement the library.
Wow, and by the way, guys, there's a ton of questions you're getting.
If you guys have more sessions, we're going to be hanging out in the Slack chat, so happy to answer them in text as we go. But
yeah, the Slack chat is actually Chumley Willem, and that's the hallway. And the one that I guess I'll ask 3 questions, and then 3 questions and so the first one is. Can you DOS this? Can you DDoS this?
The hope is no, and if you find a way to do it, submit it through our bug bounty program, and we'll pay you out for it.
There you go. So if you can do it, great. It's bug bounty. If the election got hacked already, can we assume that this would not happen again in a future election? In other words, I guess.
So something to keep in mind here, particularly with ElectionGuard, is that this is just a component that's designed to run on actual voting hardware, right? Like it's not a complete solution. So in some respects, particularly on the input to the ballot selections, we are dependent on the host system giving us good data, right? We can really only verify the chain of a particular piece of data from the time that it's passed into us until the time that it gets published as a result, right? So any attacks that you're going to have against, Windows 7 are still going to exist, right? We can't really solve those problems. This doesn't fix that. So good system design is still really, really, really important when it comes to using ElectionGuard.
Yeah, though I will also say we tried to make this secure by design when used intentionally, but also difficult to misuse. So that user error or deployment error of someone picking up this SDK and using it improperly should be hard to do.
Right.
To help prevent some of those errors as well.
All right, and then the last one, I think I got I did get one more, and it was out of band. You're not going to see it in your hallway. It showed up in my hallway, and it was basically, can you vote? You know, since this is an SDK, I think the answer is yes. But can you vote anywhere? Like, can you vote on an iPhone, Android? Is the idea to do it? I would imagine the election officials would want to vote, would want to have you physically there.
So
in a post-COVID world,
that's certainly one of the use cases that we're hoping to design for with the C++ SDK and targeting ARM, right? So we want to be able to use a mobile-like platform to be able to generate those encryption representations and have that be performant. But from there, it's really up to the companies that build election systems whether or not they're going to support that, right?
Yeah, and I'll just chime in that I think all elections officials and anyone that's sort of deeply involved in the election security space will tell you that we're not ready to vote mobily yet. There's very little traction for mobile voting. It sounds like a great idea, but the more you peel it back, just the lack of device security becomes an increasing problem.
Everybody just says, "Oh, just do a blockchain. What's the big deal?"
Right. It sounds appealing certainly, but the security implications are pretty great, and we're just not there. I don't think anybody is there either technically or from a sort of policy and election official buy-in.
Yeah, there might be some jurisdictions, but here in the U.S., it's like not even on the table, it seems, right?
Yeah. Okay. Well, thanks, team. And if you please fill out the survey. If this was a interesting thing for you all, I have to thank Microsoft, especially for having them come out and do this. So thank you, Ethan, for making that happen. And Matthew, being not necessarily employed by Microsoft, it might have been easy to get you, but thank you for giving us your viewpoint, and especially around this. I think personally, as just a red team person, what makes this fascinating for me is the fact that it's using encryption and it's trying to be secure. So if somebody actually finds a way to break this, that's interesting. If you can break a PHP app, well, it's PHP, it's broken anyway. But if you can break this, that's interesting.